Theorem 5.1, this is the page number 85. Two distinct lines cannot have more than one point in common. Two distinct lines cannot have more than one point in common. This is one line AB and here it is a CD. This is a common line E. E lies on AB as well as on the CD. We have to prove that only E is the common point. Here we are given two lines here and M. We need to prove that they have only one point in common. For the time being, let us suppose that the two lines intersect in two distinct points, say P and Q. So you have two lines passing through two distinct points P and Q. But this assumption clashes with the axiom that only one line can pass through two distinct points. So the assumption that we started that the two lines can pass through the two distinct points is wrong. One axiom is there. Suppose here it is a E and here it is a F and it is the D and it is the C. We suppose that this line CD is passing through one more point F, but we have an assumption that from 2 points only one line can be drawn. So this is wrong. So our assumption is wrong that two lines intersect at two distinct points is wrong. For this we can we are forced to conclude that the two distinct lines cannot have more than one common point. Now exercise 5.1 is there. There are some questions. 7 questions are there. You have to solve all the questions of this exercise. Equivalent version of the Euclid's fifth postulates. 5.3. Equivalent version of Euclid's fifth postulates. Euclid's fifth postulate is very significant in the history of mathematics. Recall it again from section 5.2. We see that by implication, no intersection of lines will take place when the sum of the measures of the interior angles on the same side of a fallen line is exactly 180 degrees. There are several equivalent versions of these postulates. One of them is Playfair's axiom, given by a Scottish mathematician John Playfair in 1729. He stated below: for every line L and M, for every line L and for every point P not lying on L, there exists a unique line in passing through P and parallel to L. The statement is for every line L, and for every point P, which does not exist on the line L, there exists one line passing through the P and parallel to L. From figure 5.11, you can see that of all the lines passing through the point P, only line M is parallel to the line M. Other lines may also can pass through the point P given, but these lines are not parallel to line L. Only the line M can pass through P and parallel to L as well. This result can also be stated in the following form. Two distinct intersecting lines cannot be parallel to the same line. Two distinct intersecting lines cannot be parallel to the same line. Next page 87. Euclid did not require in fifth postulates to prove his first 20 theorem. Many mathematicians, including him, were convinced that the fifth postulate is actually a theorem that can be proved using just the first four postulates and other axioms. However, all attempts to prove the fifth postulates as a theorem have failed, but these efforts have led to a great achievement: the creation of several other geometrics. These geometrics are quite different from Euclidean geometry. They are called non-Euclidean geometry. Their creation is considered a landmark in the history of thought, because till then everyone had believed that the Euclid was the only geometry and the world itself was Euclidean. Now the geometry of the universe we live in has been shown to be a non-Euclidean geometry. In fact, it is called a spherical geometry. In a spherical geometry, lines are not straight, they are parts of a great circle. That is, circles obtained by the intersection of a sphere and planes passing through the center of the sphere. In 5.12, the lines AN and BN, which are part of the great circles of sphere, are perpendicular to the same line AB, but they are meeting each other. So the sum of the angles on the same side of a line AB is not less than 2 right angles. In fact, it is 90 degree plus 90 degree is equal to 180 degree. Also note that the sum of the angles of the triangle NAB is greater than 180 degree. That is, angle A plus angle B is equal to 80 degree. Thus, Euclidean geometry is valid only for figure in plane. On the curved surface area, it fails. Now, let us consider an example. Example number 3. Consider the following statement. There exists a pair of straight lines that are everywhere equidistant from one another. Is that statement a direct consequence of Euclid's fifth postulates? Explain. Solution. Take any line L and the point P not on the line L, then by Playfair's axiom, which is equivalent to the fifth postulates, we know that there is a unique line M through P which is parallel to L. Now the distance of a point from a line is the line length of the perpendicular from the point to the line. The distance will be the same for any point on M or L and any point on L from M. So these two lines are everywhere equidistant from one another. Remark, the geometry you think will be studying in the next few chapters is Euclidean geometry. However, the axioms and the theorems used by us may be different from those of Euclid. Now example 5 exercise 5.2 is there, and there are two questions. You have to solve all the question of this exercise, and hence here the summary is there. You have to memorize all the summary. And chapter number 6 is there.